In this lesson, we're going to go over how to find the area between curves. This definition says if f and g are continuous on a closed interval from a to b, and f is greater or equal to g for all the values x which are in that closed interval, the area A, bounded by the curves f and g, and also by the vertical lines x equals a and x equals b, is going to be given by the integral from a to b of f of x minus g of x dx. So here we have a diagram. You can see that f is greater than g over the interval from a to b, and we're finding the area in between the two curves. So essentially we're taking the area under f minus the area under g, and that will give us the area in between. This example says find the area of the region bounded by the graph of f of x equals 3 and g of x equals x squared. So part A, we want to sketch the two graphs. We have g is x squared, so you have a parabola with vertex at 0, 0. It follows the pattern over 1 up 1, over 2 up 4 on both sides. Then you have the horizontal line y equals 3. So I put the 2 points right here where the graphs intersect, and then you can see the area in between the two curves. Find the x-coordinate of the points of intersection. So to find the x-coordinate where the two graphs intersect, we're going to set these equations equal to each other. So we're going to go x squared equals 3. So I wrote that here. We're going to solve for x. So we're going to take the square root of both sides. So we get plus or minus root 3. So right here where these two graphs intersect, that's going to be negative root 3. And then right here, it's going to be positive root 3. And now we want to find the area between the two curves. So we're going to integrate from negative root 3 to positive root 3, and then it's going to be the top curve minus the bottom curve. So for this shaded region, you have your top curve is y equals 3, and your bottom curve is going to be y equals x squared. So to set this up, we're taking the integral from negative root 3 to positive root 3, and then we do the top curve minus the bottom curve. So here's our integral set up. So I labeled this y sub t, and this is y sub b. So this is the y equals the top curve, and then y equals the bottom curve. So at this point, we can integrate this, but you'll notice if we integrate from negative root 3 to positive root 3, this area right here is equal to this one. So integrating from negative root 3 to positive root 3 is the same as integrating from 0 to root 3 and then timesing by 2. And that's going to be convenient in this specific problem because when we integrate this and then we evaluate, we plug in the upper limit minus the lower limit, plugging in 0 is always a little bit more convenient. But again, you could totally just integrate this as is and you'll get the same answer. I made a note over here, this shaded region, or that area, has y-axis symmetry, and that's why we're able to rewrite this as 2 times the integral from 0 to root 3. So now we're going to integrate. So once you integrate right here, you're going to plug in root 3 minus plugging in 0. So I plugged in root 3 here and here, and then if you plug in 0, you're going to get 0, so I didn't write that down. And then at this point, I'm going to rewrite this 3 times over here. And you have 3 3's underneath the radical, so 2 of them come out to just be 3 root 3, and now these 3's are going to cancel. So you have 2 times 3 root 3 minus 1 root 3, and those combine to make 2 root 3. So our final answer for this area is going to be 4 root 3. Here I have a note. It says to find the area when f is not always greater than g. You can break it up by sections. So for our diagram, I have f right here, and then I have g right here. So you can see the two graphs intersect right here, and I labeled that c on the x-axis. So if you wanted to, you could set up 2 different integrals and add them together. So the first integral would be from a to c, and it would be f minus g. And then you would add the second integral, which would go from c to b, and it would be g minus f. So that's one way to do this. And on a graphing calculator, you would just do the integral from a all the way to b, and you can use absolute value of f minus g, and this will give you the same answer. This example says, given the functions f of x equals sine of x and g of x equals x cubed minus 2x minus 1, approximate the x-coordinates of the points of intersection of the curves, and then find the area of the region bounded by the curves. I put this as my y1 into the graphing calculator, and then I put this as my y2. So again, y1 and then y2. And when you hit graph, you can see that your sine curve, it goes through the origin, and your cubic function goes like this. So you can see the two regions bounded by the two curves. So next we're going to find these different points of intersection. So I'm going to label them. So this first point of intersection is x sub 1, then the next one's x sub 2, and then the third one is x sub 3. So we want to find x sub 1, 2, and 3. So you can see I have sine of x as y1, and the cubic function is y2. I'm going to hit zoom, and then standard number 6. So here you can see the two graphs. So it graphs the two equations out on a negative 10 to positive 10 xy axis. And next we're going to find the points of intersection. So we're going to go second trace, and then we're going to do number 5. intersect, and we're going to arrow over to the first intersection, which is right about here. It's asking for the first curve, so we press enter, then the second curve, press enter, and then guess, press enter. So we're rounding to 5 decimals, so the first intersection is going to be negative 1.41102. I'm going to hit trace again, and then we're going to move over to the next x-intercept. We're kind of close to it, and we're going to do that again. We're going to press second trace, or second calc, and we're going to select 5. And first curve, press enter, second curve, enter, and then guess, enter. So our next x-intercept is going to be negative 0.34999. And we're going to do this one last time. We're going to press trace, arrow over, and again we're going to go second and then calc, number 5, and then press enter, enter, enter. So our last x-intercept when we round to 5 decimals is going to be 1.7667 and then 0. So now that we have the 3 x-intercepts, we're going to press the math button, and then we're going to do 9. And first I want to demonstrate integrating from the first x-intercept to the second one. So the first x-intercept was negative 1.41102, and then we're going to integrate to the next one, which was negative 0.34999. So in this little region, the top curve is the cubic graph minus the sine curve. So that's what we're going to do here, and I just want to go back to y equals. Again, it's the cubic minus sine, so it's going to be y2 minus y1. We're going to press alpha trace, and we're going to pull up y2 minus, and then alpha trace, we're going to pull up y1. Alright, so we have that set up. So now we're going to add the next integral. So we're going to go math 9 again. And this time if you look at this picture, we're going from x sub 2 to x sub 3. And the top curve is the sine curve minus the cubic. So I got the x-intercepts in there. It was the second x-intercept to the third one. And then this time we're doing y1 minus y2. So we go alpha trace, we pull up y1, minus, and then alpha trace, pull up y2. So we just press enter and it kicks out our final answer. It's 4.418. And again, the shaded region plus this one is going to be the 4.418. So I have this written out here. We have the integral from x sub 1 to x sub 2, and again it's g minus f. G is the cubic function minus f is the sine curve. And then we add to that the integral from x sub 2 to x sub 3. So again, that's from here to here. And we have these values listed here. And then for this shaded region, it was the sine curve minus the cubic. So it's f minus g. We plugged that all in the calculator and we got 4.418. And I made a note here, we can also evaluate this total area, meaning both of these, using absolute value. So you can do the integral from x sub 1 all the way to x sub 3, absolute value of f minus g, and we'll show that on the graphing calculator. So we're going to press math 9, and we're going to show that we can also do this with absolute value. So we're going to start with x sub 1, so that was negative 1.41102. And we're going to integrate all the way to x sub 3, and x sub 3 was 1.7667. And then to select absolute value, we're going to press math right here, and then arrow over, and number 1 is absolute value. And then we're going to go y sub 1 minus y sub 2. So we're going to go alpha trace y1 minus, and then alpha trace again, this time selecting y sub 2, arrow over, and press x for dx. And we should get the same answer. So we get 4.418. Alright, so when we showed it on the calculator, you could see that using absolute value also gives you the same answer. So when you have two curves where one curve is not necessarily above the other one for the entire interval, so you can use either method where you do one curve minus the other and then you flip it, or you can use absolute value. Either method works using a graphing calculator. This example says evaluate the integral and interpret it as the area of the region and then sketch the region. So we have the integral from 0 to 2, and we have the cube root of x minus x cubed. And it's in absolute value, indicating that at some point in between 0 and 2, the two curves are going to switch which one's on top. So here's our x cubed graph. Next I'm going to graph the cube root of x. But again, we only want the region from 0 to 2. So you can see from 0 to 1, the cube root of x is above the graph of x cubed. But then from 1 to 2, x cubed is above the graph of cube root of x. So we could set this up as two separate integrals. We could say the integral from 0 to 1 of the cube root of x minus x cubed plus the integral from 1 to 2 of x cubed minus the cube root of x. Or using a calculator, we could just plug this right in using the absolute value. Either method will give you the same answer. Okay, so I pressed y equals, I typed x cubed into y1, and then y2 is our cube root of x. We're going to hit graph. So you can see the two graphs. Now I'm going to go second quit, and next we're going to do math 9. And let's go ahead and integrate from 0 all the way to 2. We're going to press math. We're going to arrow to the right and select absolute value. So we do alpha trace for y1, minus, and then alpha trace, and select y2, and then press dx and enter. So we end up getting 3.110 as our total area between the two curves from 0 to 2. So our final answer for this area plus this one, again it's the area between the two curves from 0 to 2, is 3.110. Next it says to find the area between two curves that are not functions, calculate the integral in terms of y. So we have here the integral from c to d of f of y minus g of y dy. So you can see our diagram right here, we have g of y is on the left, f of y is on the right. Neither of these are going to be functions because they don't pass the vertical line test. And we can still find the area in between them. So right here on the y-axis we have c and d. And so to calculate the area in between them, you're using your formula, the integral from c to d. And it's going to be f of y minus g of y. So the way I think of it is you're integrating the curve on the right minus the curve on the left. This example says find the area of the region bounded by x equals y squared and x equals y plus 2. This graph right here is a parabola that opens right because the y squared has a coefficient that's positive. So the vertex is on 0, 0. It goes over 1, up 1, and then over 4, up 2. Does the same thing going down. And then again, I just rewrote this as y equals x minus 2, so I went down 2, and then slope is 1. And you can see the two graphs intersect here and here. So to find the area, we're integrating from a lower y value to an upper y value. So you can see we're going to integrate from -1 to +2. So let's set that up. So as far as labeling them, I put them back both in x equals form. So this curve on the right is x equals y plus 2, and the curve on the left is x equals y squared. Okay, so we have this set up, and this is x equals the curve on the right, and this is x equals the curve on the left, so that's why I put a sub r, sub l. And again, when you're setting these up, just make sure that your limits are the lower y value of the shaded region to the upper y value of the shaded region. I'm just going to rewrite this before we integrate. So I just put -y squared in the front and then drop down the y plus 2, and now we're ready to integrate with respect to y. So the integral of -y squared is -1/3 y cubed. The integral of y is 1/2 y squared, and then the integral of 2 is 2y. So I plugged in 2, and then we subtract, plugging in -1, and then now we're going to simplify. So you get 9/2 as your final answer. This example says find the area of the region bounded by y minus x equals 6, y minus x cubed equals 0, and 2y plus x equals 0. So first thing I did is I took all of these equations and rewrote them as y equals. So this one is y equals x plus 6. This guy right here is going to be y equals x cubed. So here you subtract x and divide by 2, so you get y equals -1/2 x. Next, I took these three equations and graphed them. So this equation has a y-intercept of 6 and slope of 1. Right here we have x cubed, so it's this graph right here. And finally for this equation, your y-intercept is 0 and your slope is down 1 over 2. And so you can see the shaded region that's bounded by all three graphs. I broke it up into two parts. To find the area, we're going to integrate, but it's going to be this curve minus this one. And then for this region over here, it's going to be this curve minus the x cubed curve. All right, so I have it all set up. You have your first region, you're integrating from -4 to 0. And then your second one, you're integrating from 0 to 2. And again, this is all with respect to x because it's going to be the top curve minus the bottom for both of the areas. And then now I'm just going to work it out. So right here, a negative is positive, so we have 1x plus 1/2 x makes 3/2 x. I dropped down the 6, and then over here just rewrote it as -x cubed plus x plus 6. So let's go ahead and integrate. So once you integrated here and here, you're plugging in 0, minus plugging in -4, so that's this right here. Over here we're plugging in 2, and then minus plugging in 0, so I just left that off, and then you can see our final answer is going to be 22. This example says the table shows the velocities of two cars driving side by side in feet per second for 12 seconds. Use the midpoint rule to estimate the distance between car A and car B after 12 seconds. So using the midpoint rule to estimate the distance, we can go from 0 to 4 seconds, 4 seconds to 8 seconds, and 8 to 12 seconds. So then that works out perfect because we have t equals 2 seconds, 6 seconds, and 10 seconds, ends up being the midpoint in between 0 and 4, 4 and 8, and 8 and 12. So in front we factored out the 4 because the width of each rectangle is 4, and then we have v of 2, v of 6, and v of 10. So from the chart for car A, the velocity at 2 seconds is 34, at 6 seconds it's 67, at 10 seconds it's 84. So you get that car A traveled a total distance of 740 feet. We're going to set this up the same way for car B. And from the chart, at 2 seconds your velocity for car B is 21, at 6 seconds it's 44, and 10 seconds it's 56. So you get that car B traveled a total of 484 feet. So finally, the distance between car A and car B after 12 seconds is going to be 740 minus 484, and that's a total of 256 feet. Alright guys, thanks for watching!